across the country at the Circuit of the Americas this July. Very exciting stuff. Thanks to all of these people for putting on those amazing things, stretching all the way through the foyer. And for our stars from visiting from schools, Anderson Mill Elementary, where are y'all? Okay. Austin area homeschoolers. Blackland Prairie Elementary. A smattering of applause. Lamar Middle School. More than a smattering. Laurel Mountain Elementary. Okay, well, it sounds like Laurel Mountain really carried the day here. Maynard New Tech. And Travis High School. Okay, you guys all represented well, I think is what they say. We want to acknowledge Scientific American. They are actually taking our webcast live and streaming it themselves to their channel. So we want to welcome all the viewers from Scientific American on the webcast. Hello, everyone. Thanks to Domino's for the pizza, to Environmental Science Institute staff and interns and student volunteers from the environmental science major, and Melinda, who makes it all come together, and our co-sponsors as well. Let's thank all of these people. And some special thanks to the sponsors of ESI Sustainability and STEM outreach programs, including the Mitchell Foundation, KDK Harmon, State Farm, 3M, Avon, UT Sage, and all of our generous donors and members. Thank you very much. As you guys know, thank you. Yes, let's hear it for them. As you guys know, special programs such as this are not part and parcel of the normal stuff that happens at a university, so we really rely on generous people, folks, and foundations to help with this. And if you're asking, how can I help ensure the future of Hot Science School Talks, you can hit this button, Give to ESI. Where would that button be? You could follow us through all these social media outlets. How can you do more than just follow us? You can give contributions. You can click on Give to ESI by going to this address, hotscienceschooltalks.org, or you could see the environmental science students with this bright smiling faces and the EVS t-shirts on your way out this evening, or you could volunteer. If you're interested in any of this, send a message to this email address. If you aren't fast enough in copying this email address down, see one of us after the talk, either me or one of the environmental science students. So please remember to turn off all electronic devices. There's no conversations during the lecture. The program includes a Q&A session that I promise will be very lively. And the whole thing starts at 7 now, and it ends at 8:15. We'll be going straight through to then. I appreciate your patience on all of this. And I want to give you, before we start, a very quick by-the-numbers history of Hot Science School Talks. It was founded in November 1999 in a 300-seat auditorium in the Geology Building. 600 people showed up that evening, so we quickly had to find another space, and now we're finding we have to find probably another space beyond this 500-seat auditorium. 94, what's that number? 94, this is the total number of Hot Science School Talks that have ever been presented. We're closing in on 100. 94, that's a lot. Number 4, what does number 4 mean? That's the number of people who have presented 2 Hot Science School Talks. So to present 1 Hot Science School Talk, we have a pretty high bar. You have to be a dynamic speaker. You have to be a leading researcher. You have to value the value of outreach and community engagement. Suffice it to say, I've never come near that bar. So it's filtered me out effectively and many other people. You really have to be pretty special to have done it even once, but to do it more than once, you have to be twice as special. So number here, 2, that's the number of people who have presented 3 Hot Science School Talks. Wow, now it's getting geometrically impossible to attain this level of passing the bar. And we're down here to number 1. What do you think 1 is? The number of people who have presented 4 Hot Science School Talks is 1. That person is Michael Weber. Wow, and he hasn't even said a word yet. That's pretty good. There's another number 1 here. I find there's a number of similarities between Hot Science Cool Talks and the Academy Awards. It's eerie how many similarities there are. There have been 94 Hot Science Cool Talks. That rounds down to 90. In 48 hours from today, that's really eerie too, there will be the 87th Academy Awards. That rounds up to 90. I mean, it's just too crazy to be just coincidence. But here's one more. It's this number 1. The number of actors or actresses who have won 4 Academy Awards for Best Actor, Actress. One person has won 4 Academy Awards. Who was this person? Liza Minnelli? I don't think so. No? No, it was not Vin Diesel. No? All right. Are you ready? Here's the answer. Here's the answer. It's Katharine Hepburn. Well, so bottom line is I could regale you with all kinds of awards for excellent teaching that Dr. Weber has won, all of his research accomplishments, the hundreds of publications he's published, and recently becoming a fellow of the American Society of Mechanical Engineers, a very high honor, which he received last year. I could go on and on about all of his awards, but I think it's probably most appropriate just to say, please welcome the Katharine Hepburn of Energy, Professor Michael Weber.
Now can you hear me? Is it too loud now? Yeah. Did you hear my offensive jokes earlier? No, the mic was off, so you didn't hear them. We too loud? We got feedback now? No, I turned it down a little bit. I'll keep talking until you get the volume right. Your television production's difficult. That's one of the things we learned. All right, is that better? Okay. I'm not allowed to press any buttons. One thing you learn in the energy industry, if you're around power plants, don't press any buttons if you don't know what they do, especially at nuclear power plants. So that's why I'm not trusting anything. Let me tell you, maybe I'll back up and say, we're here to talk about energy. Let me tell you about Rick Smalley. Rick Smalley, a brilliant thinker, a Nobel Prize winner, a professor at Rice University who discovered buckyballs, these very complicated chemical structures. And I like chemists because of my father and all the chemistry teachers in the room. And he spent the last 10 years of his life giving many speeches around the world about the society's 10 grand challenges. And he listed them in order of most important to least important, although they're all important, but from most important down through 10. And it starts with energy at the top, then water, food, the environment, poverty, terrorism and war, disease, education, democracy, and population. And he put energy at the top with the idea that these are sorted in order where if you solve one, it solves the next. If we can solve our energy problem, then we'll have plenty of clean water. And if we have energy and water, then we can grow all the food we need. And if we can have energy, water, and food the right way, we can protect the environment. If we do that, then we can raise people out of poverty and so forth. So these are listed in order of the grand challenges and the pathway by which we need to find solutions. Energy's at the top, so energy is important. We like energy. Energy is cross-cutting. It touches just about everything in society. It's relevant to transportation and our cars and electricity and food and water and industry and our homes and businesses. So we like energy. It touches everything. It's relevant to the issues we care about, like the environment and public health and education and national security and poverty. So energy touches everything. It's important. We have to take it seriously. It's at that top of the list of our grand challenges. And it is good. Energy is good. It gives us abundant food and clean water and productive industry. It makes us rich if we do it the right way. It gives us social mobility and physical mobility. We can move up the ladder or across the country, and it gives us comfortable buildings. We can cook and light things. So we like energy. And the energy that we think about has many scales. And we think about power as well. Power is actually the rate of energy, the rate of energy production, or the rate of energy consumption. And that's power and the power trip. And that rate becomes important, and that rate has many different scales. There's a watt. You might have heard of a watt, or a kilowatt, or a megawatt, or a gigawatt, or a terawatt, or a petawatt. And this is a watt, and 1,000 watts, and a million watts, and a billion watts, and a trillion watts, and a quadrillion watts is a petawatt. So there's many different scales that are relevant for energy, and I'll walk you through some of them. An average person consumes energy at a rate of about 100 watts. So all of you right now, about 100 watts. Maybe I'm 110 watts because I'm talking, and just because I'm bigger than most of you. But let's say 100 watts. That's the rate at which humans use energy. A trained Olympic athlete at full speed is something like 400 watts. Like a great cyclist or a great athlete, 400 watts. So that's the scale of power consumption within a human body. And to think about that, that human athlete, that Olympic athlete, could operate at 400 watts for 2.5 hours, would generate a kilowatt hour of electricity that's worth 10 cents. So imagine having an Olympic athlete as a servant pedaling for 2.5 hours just to make you 10 cents worth of electricity. That's the way the energy system is today, where we have these servants, coal and natural gas and oil and biofuels, all these things giving us the equivalent of all this power, this human power. So that's a human, 100 watts. Go to a horse. A horse is about a horsepower, about 750 watts. And 1 horsepower is 746 watts. So a horse can do the power of about 7 to 8 people. They can carry more things and lift more things. So we like horsepower, so that's bigger. Then you get to a square meter of sunshine is about a horsepower, about 750 watts per square meter. A meter is about the size I'm standing in around me. And if you put that out in the northern hemisphere, you get about 750 watts for that square meter. So that gives us some sense of how much energy we can get from the sun. A hairdryer needs a couple meters of solar power just to dry your hair, or you can go stand in the sun just to get your hair dried that way, another option. A car, here's a Toyota economy car, 106 horsepower, 79,000 watts, 79 kilowatts. Here's a race car. I put that in there for my son Maverick because he likes race cars, but he would have preferred a Ferrari, but I did a Dodge Viper. So a Dodge Viper, almost 500,000 watts, 640 horsepower, fast car. Then we have a standard wind turbine, 1.5 megawatts. These are big, 1.5 million watts. And then 4,000 horsepower, 3 megawatts for a diesel-electric locomotive. You get to a Boeing 747, 140 megawatts, 4 big engines. UT, by the way, is like 60 megawatts just to operate UT campus. So this is a scale of power. We get to the Hoover Dam, about 2 gigawatts, 2 billion watts. We get a power out of that. A space shuttle, I put that in for my other son, David, because he's talked about being an astronaut. 11.7 gigawatts, 11.7 billion watts of power. That's a lot of humans to lift that into space. We can talk about U.S. power consumption overall, 3.34 terawatts, 3 trillion watts for everything in society in the United States. You go to the globe, 17.5 terawatts. We're like a fifth of the globe's power consumption is just in the United States. The whole globe for everything we do, all those lights, all those video games, all the things we do, 17.5 trillion watts. The numbers just keep getting bigger from that 100 watts to now trillions. And then you get to the world's most powerful laser. It's actually here at UT, and that's 1.1 petawatts, 1.1 quadrillion watts. That's a lot of power. Now, it's for a split second. We don't do it all the time. You turn it on and off really fast. That's a lot of power in a small amount of area and a small amount of time. And then you get the sun, all the sunshine coming to Earth, 174 quadrillion watts, 174 petawatts. So we need 100 watts for me, and you add up all of us, you keep multiplying that to get to the entire Earth, and then we have 10,000 times more energy hitting the Earth every day than we need to power all of humanity. So the bad news is we use a lot of energy. The good news is we got a lot of sunshine. Maybe we could use that. So that's one of the glimmering hopes of the future. We might have other options, just for the sense of scale. And we like energy because energy and affluence, energy and wealth go hand in hand. On the y-axis, up and down, that's the wealth in dollars per person around the world. And the energy consumption on the x-axis is consumption in million BTU of energy per person per year. A BTU is a British thermal unit of energy, and a million BTU is just a million of that. And a BTU is about the same energy in a kitchen match. So a million BTU is like a million kitchen matches worth of energy. And the richer countries that are higher up tend to be over on the right. They tend to use more energy. So richer people use more energy, or people who consume more energy get richer. It's not clear what causes what. Do we use energy because we're rich, or are we rich because we use energy? But somehow they go hand in hand. Not perfectly. Here's the United States. We're pretty rich, and we use a lot of energy. Here's the United Kingdom. They're almost as rich, but they don't use quite as much energy. So maybe there's some trade-offs we could go where we could stay rich and not use as much energy. And there's disparity around the different nations. Iceland uses a lot of energy. Iceland's really cold, so they want energy to warm themselves up. And they've got free geothermal energy coming out of the Earth because they're on the Mid-Atlantic Ridge. They've got volcanic energy, and they use that for free to heat themselves up. So Iceland uses a lot of energy per person. The map of the world, if we look at it at night, it's a picture of the Earth at night. The map of lights is the map of electricity. And the map of electricity is the same thing as the map of wealth. The lights are where there's electricity, there's wealth. So these maps are identical. And you can see things like the Nile River in northern Africa. You can see the United States and the eastern seaboard and all of the cities. You can see how dark it is in the Amazonian jungle in Brazil where there are no people. You can also see places where there are people, but they're poor and it's dark. Let me give you an example with this satellite video from NASA flying east over Asia. All those lights are people and cities and money and wealth. That's in China that we're passing over, and we're coming up on the Korean Peninsula. You know, see in the upper right a lot of lights. That's South Korea. The bright spot is that's Seoul, and in the north that is dark. That's North Korea. It is poor. Those are people. They don't have money. They don't have democracy. They don't have electricity. Electricity, wealth, democracy go hand in hand. The difference is the borders with China and South Korea. So we like energy because it gives us things we like. It gives us liberty. It gives us some democracy. It gives us a chance for education and affluence. It's a good thing, but it also has some downsides. As much as we like energy, we have to worry about its national security impacts. Are we buying energy from people who hate us? We have to worry about environmental degradation. Are we burning or using energy in a way that overcomes the limits of the atmosphere of the oceans to take up the waste? And we have to worry about the economic effects. Are we going to run out of the stuff we like at the price we like it, in which case it will affect the economy? So we have to think about finding energy solutions that meet all our desires for the economy, the environment, and national security. That's the challenge. Managing the good and bad of energy is the grand challenge of the 21st century. And as Professor Rick Smalley said, it's the most important challenge. Once we solve that, we can move on to the others. That's why we're here tonight. So what is the status of energy today? Well, I'd say energy has some change afoot. Changes are about to happen. And I want to start with some fun facts about energy. Surprising things you might not know. About 10% of all the energy we consume in the United States is in the food we eat, and all the energy that went around making the food, growing it, harvesting it, chopping it, moving it to market, freezing it, boiling it, then throwing it away. 10% of our energy consumption is just going to the food system, and then we throw away a fourth to half of all our food. We're throwing away energy embedded in that food. There is enough energy in the food we throw away, and all the trucking and all the refrigeration that went around it, to power Switzerland for a year. That's a lot of energy. Just to give you a sense of scale. Like, we consume a lot of energy. We consume a lot of it for food, and then we throw a lot of that food away, which is really sad to me. So something to keep in mind. We spend 1/3 of all our energy boiling water. Can you believe that? Just boiling water at power plants. So we take water, we boil it. We use energy to boil that water to make steam. That steam spins turbines. The turbines spin a shaft that spins magnets. That makes electricity. So we're spending 1/3 of the nation's energy just to boil water at power plants, just to make electricity. That is a robust way to make electricity. We do a lot of it. We spend about 13%, like 1/6 or so of our energy just on water to heat it, treat it, pressurize it, chill it, move it to our homes, and then take it back to the wastewater treatment plant through the toilets. It's kind of gross to think about. Treat it again and then put it back in the rivers. So we spend a lot of energy on our water. And we spend a lot of water on our energy, by the way. About half our water withdrawals every day are just to cool power plants. So we use a lot of energy for water and a lot of water for energy. We have so much energy embedded in our water. We use more energy through our taps and shower heads than in our light bulbs. And we have so much water embedded in our energy. We use more water through our light switches and outlets than through our taps and shower heads. This is kind of a confusing idea, but when you flip a switch for electricity, a power plant gets activated somewhere else, and there's water at that power plant to cool it. So that light switch is activating a water system. And when you turn on your faucet to get water, it's activating an electric water heater or electric pump or some electricity somewhere, some energy system somewhere, and that's driving up our energy consumption. Kind of a surprise about how energy is connected to everything. In many parts of the world, it's the woman's responsibility to get water. So those water pumps, water heating becomes important. In poor parts of the world, women walk miles to get water, carrying buckets of water on their shoulders or on their head. Then they walk miles to get fuel wood or cow dung that they burn to boil the water to treat it, and they burn it in inefficient cook stoves. And unfortunately, that dirty wood and the dirty cow dung burned in a dirty stove kills a couple million women and children prematurely every year. If we could just improve how women get water in Africa and Asia, it would save millions of lives a year. That's the prototypical image of a poor person, is a woman carrying water on her head. That's an African woman or an Asian woman, but that was an American woman 80 years ago. This is the Farm Woman's Dream, an American rural agricultural promotional poster called the Farm Woman's Dream, encouraging people to electrify out in the farms of the United States, saying, your women are carrying water in the cold uphill, manually pumped. It's so hard to do, and then it's cold, and they could have, up in the dream, you see it hot water piped there. They use electricity to pump it and then to heat it. So in this way, electricity is liberating. In particular, it liberates women because it relieves some of the chores that women had been having responsibility for. So that liberty of having the electrified water, energized water, had repercussions in the United States, and it will in other countries as well. We forget, we think that's just something for poor countries, that's something for people across the globe. That was us not so long ago. So energy is important because it liberates us. And those energy situations change. So we like energy, it's good, it's got these downsides, and energy situations change. Here are the headlines from a decade ago. The end of the oil age, we're running out of oil, we're all gonna die. The end of cheap oil, it's gonna get expensive. After oil, powering the future, and you can't really see it, but the subtitle is The Bomb, 60 years later. Not an accident that there's an article on nuclear power in a cover about oil. So energy, we're running out, but those headlines have changed, and now it's America strikes oil, or fossil fuels, we'll never run out of oil. Like, it's all good news. We've got more than we know what to do with. Do you believe we'll never run out of oil? Yeah, it's kind of, so, well, maybe we got a lot of it. There's a lot of stuff out there, but it's hard to say we'll never run out. And here it is, why the fossil fuel boom is good for America, bad for Saudi Arabia, and scary for the planet. Bad for Saudi Arabia. Saudi Arabia doesn't want us to produce so much oil, so now there's a battle, sheikhs versus shale. Saudi Arabians in competition with Texan oil producers. That's a Texan over there on the right. And they're both pumping their gasoline. That's just a couple months ago. That's just end of 2014 when the shale boom had really worked. We got all this energy we're producing at home. And what does that do? That causes worldwide prices for oil to collapse. Prices have gone up from $40 a barrel to $100-something a barrel for Brent crude or for West Texas Intermediate crude. Prices plummeting towards the end of 2014 because of a market share war between the Saudis and everyone else, including Texans. So everyone around the world wants to produce oil to make money, but if you have everyone doing it, you got more oil than there are customers and the prices collapse. So that's what's happening right now. Energy situations change. And there's some good news economically. There's also environmental concerns. With natural gas and oil production from shale, you have to worry about flaring. All this extra gas that comes out, people burn it for safety reasons. You don't want loose gas around. You want to burn it so it doesn't explode. And those flares are like 20 feet tall. You can see them from across the prairie. In fact, you can see them at night from space. So here's the United States at night. Here's New York City up on the right. Here's Chicago. Here's Dallas. And here's Houston and San Antonio and Austin and that kind of thing. You can see the different cities at night. Let's zoom in just on Texas. Here's the map. San Antonio, here's Houston, here's Corpus. And look at that map at night in 2000. So well over a decade ago. In 2000, this is the map at night. There's San Antonio and Victoria and Houston and Corpus Christi and Loretto. And let me show a map that's updated to 2012. Those lights, that's the Eagle Ford Shale. Those are not people. Those are flares from the natural gas in the oil production in the Eagle Ford Shale. We can see the flares at night. That's one of the environmental impacts. You can see it from space. Holy cow, all that burned off gas. That's a lot of energy. Makes me kind of sad to see all that wasted energy. That's a problem we need to solve. Yeah. Here's North Dakota. I agree. Can I get a hallelujah with that? Yeah, so we're doing the preacher session later. So yeah, kind of like, here's Williston, North Dakota. Has anyone been up there to that corner of the world, the Bakken Shale? A few of you have. Not many. It's not a typical place people travel. That's because there aren't many people there. Here it is at night. Those are flares. Those are not people. The city is right there. So a lot of flared natural gas. So this is one of the environmental downsides of shale production. And the other thing to keep in mind is energy technologies change very slowly. We have change. Prices might change from day to day, but the technologies evolve very slowly. We have some great technologies, but it turns out that just 4 technologies are responsible for 3/5 of all the energy conversions in the world. We have the steam turbine. I told you about all the energy for boiling water for the steam turbine to make electricity. There's the gas turbine. We use gas turbines to make electricity. We also use them on planes to fly. You either put a nozzle on it or a generator. So there's a gas turbine, a spark ignition internal combustion engine, that's ICE. That is a gasoline engine, or a compression ignition internal combustion engine, that's a diesel engine. So we've got 2 engines for cars and 2 engines for planes and power plants, that's it. And those were all invented in 1893 or earlier. 3/5 of the world's energy conversions happen with technologies from the 1800s or 1700s. It's been a while since we've had a breakthrough, I would say. So we need some more innovation. We have old technologies powering a modern economy. We could look at something new. Let's talk about wind generators. Wind generators are new. Those were invented in 1888, so we could try that. Solar cells are really cool. We like those. 1883 by Charles Fritz, so even those aren't new. What about space age stuff, the fuel cell? We've got to go to fuel cells because this is the newest, greatest stuff, and those were 1839. Space age technology was around for 100 years or more before we had the space age. So let's try electric cars. Any fans of electric cars? Anyone own one or want one? You like that? Electric cars are fun. My next car is an electric car. I've got a hybrid now. I'm getting an electric car next. Electric vehicles are brand new. They never thought of, well, at least not since 1839, when James Joule, a unit of energy, a great thermodynamicist, said, I can hardly doubt that electromagnetism will ultimately be substituted for steam to propel machinery, saying that electricity will replace heat for driving our machines like our cars. That was before there were even cars. Boy, was he right. It's just taking a couple hundred years. So these things take a while, and I'm hoping someone in the room will be that innovator that takes us to the next level. The other part of transition is they've happened before. This is United States energy consumption by source over time from 1800 through today. And there's a variety of eras and fuels. Petroleum's at the top for today. Here's petroleum, natural gas, coal, renewables, and nuclear. And petroleum's king. We use a lot of petroleum because we like petroleum. It gives us mobility, lets us move our cars. And then natural gas, coal, renewables, and nuclear. But there's different eras. If you back up to the 1800s, wood was dominant. We used wood to make fence posts and to build our homes, and we burned it for heat in our homes, in our fireplace. And we even used wood. We would char it and burn it to melt metals and that kind of thing for industry. So we used wood. That was dominant. Until 1885, coal was dominant. Coal came along, better fuel actually, better energy density, a little cleaner, produces less ash and less smoke and less CO2, and it was cheaper and it was closer. The wood ended up being like several states away, but you might mine the coal right there in Pennsylvania if that's where you live. And coal was dominant from 1885 to 1950, at which time petroleum became dominant because petroleum came along and we could use that for cars. We could use coal for metal making, we could use coal for heat, we could use coal for steel making, we could use it for power, but we could use oil for cars. So now petroleum's dominant, but look, petroleum's dropping the last few years and natural gas is rising. So maybe the next era will be natural gas, or maybe that'll last a couple of decades and we'll move on to something else, nuclear, renewables, bioelectricity, like electric eels that we hook up to our home to operate our lamps and things like that. So something else is coming, an energy transition is coming. It has happened before. That's part of what happens with transitions. Usually, it helps us out. Here's the use of wood across the United States. That's the acres of forest from 1620 to 1850 to today, 1920. We cut down all the forest. We were cutting down the forest because we're using that wood for energy. And we're cutting down the trees faster than they grew back. If you've ever been to the upper Midwest, Minnesota, Wisconsin, or New Hampshire, in New England area, all these beautiful forests, thick woods, those are all new trees, all regrowth, second growth forests in the last 150 years or so, because we cut the trees down. We deforested the nation until coal came along, and coal was better, and coal saved the forest because we started using coal instead of wood. And that's really hard for us to interpret today, because today people think of coal as a threat to the forest from mountaintop removal mining or from acid rain, but 150 years ago, coal saved the trees. Isn't that amazing? Same kind of idea with whale oil. We did a lot of whaling. We liked whale oil as an illuminant. We'd burn it for light in these whale oil lamps. But the whale oil smelled like bacon, or sort of pungent smell when you burn it. And it was hard to get, and we were running out of whales. We had peak whale in the mid-1850s. As we were running out of whales, it got more expensive to get whale oil. We found something better. 1859 in western Pennsylvania, we drilled for oil and found oil. And oil was a better fuel. And you take a barrel out, and in the middle of that barrel was a slice of kerosene that burned brighter and hotter and longer and cheaper and with less smoke than whale oil. So it was a better illuminant. It was used for lighting up with these kerosene lamps. So kerosene came along, so oil saved the whales. And we think today of oil as a threat to the whales from oil spills and everything else. But 150 years ago, oil saved the whales. Yesterday's solutions are today's problems. That's one of the things about transitions. They take a long time. We move towards something better, but then we have problems from that when we use a lot of it. Today's solutions to the problems of oil and coal will be tomorrow's problems. So we do a lot of something, we solve one problem, we move on to the next problem. So keep that in mind. Coal and oil, a lot of people think of are bad, but they've done a lot of things for our economy. They save the trees and whales, but now we have new problems from them we didn't know about 150 years ago. Namely, we have to worry about CO2. And CO2 is interesting because the carbon intensity, the amount of carbon dioxide emitted when the fuel is burned per unit of energy has dropped over time. Wood is more carbon intensive than coal, is more carbon intensive than petroleum, which is more carbon intensive than natural gas. And so as we move from wood to coal to oil to gas, we have actually decarbonized society. We're releasing less carbon per unit of energy consumed. And that's a good news story. Now, we've consumed more energy, so the total carbon's gone up. Until the last few years, we actually turned the corner, and now our carbon emissions are dropping because we're using more natural gas and less coal in the power sector. But this is part of the trend. We're cleaning up as time goes on. That's not a political invention. That's something societies do as they get richer. They clean up their act, so to speak. So the carbonization has dropped, which is great news. And that change of energy over time is a marker. We can use our energy system as a marker of where we are in the old days or medieval ages or modernity. The types of energy has changed. In the old days, the medieval times, we use a variety of forms of kinetic energy, like windmills and water wheels. And we use sails for transportation. We use muscle power, like humans dragging things or horses dragging things. And we do that for moving goods or sawing wood or grinding grain or polishing glass. So we would use these medieval forms of kinetic energy to achieve a lot of useful functions. And we also have medieval forms or primitive forms of thermal energy, like wood and charcoal and peat and dung like cow patties and straw. We would burn them and we'd use them for cooking and making glass and boiling soap and making lime. So we had different types of energy than we do today. The type of energy we use is a time marker for where you are in the eras of civilization. The Industrial Revolution, the main enabler, the key invention of the Industrial Revolution was the steam engine, taking heat to motion. We could burn coal or dung and get motion, and that motion gave us machinery and gave us machines that we could use for textile mills and other things to cut wood at greater speed and greater rate. So that was the enabler for the Industrial Revolution. And now we have the modern era, the modern history, it's fossil fuels. The defining element of the modern era is we are the oil era, the coal era, the natural gas era. So that's how we differentiate modernity from antiquity or the medieval times. So we use a lot of fossil fuels. Well, what about the future? Well, that's today. What are we going to do about the future? Well, moving into the future, we got to make predictions. It's tough to make predictions, especially about the future. That's what Yogi Berra said. It's much easier to make predictions about the past, but even those are wrong sometimes, so you got to be careful. So we got to think about the future. As we make our options for fuels and technologies for the future, we have to keep some trade-offs in mind. We talked about these earlier. We have to pick energy systems that don't undermine our national security, that are of sufficient supply to be good for our economy, and that don't trash our environment. We want energy that's good for our environment, good for national security, and good for the economy. And the challenge is most of the options are good for one or two, but not all three. Coal is abundant and cheap, but not good for the environment. Coal is also good for national security because it's domestic. Biofuels are domestic, so that's good, but they tend to be expensive. So we have these challenges where we can solve one or two. How are we going to get to all three? Well, good design, good integrated engineering design, good innovations. As we move forward, though, we've retained this issue of energy inequities that are a vexing problem. We're rich in the United States, but more than 12% of the world population is undernourished and hungry. 12% of the world population lacks access to improved drinking water sources, clean water, piped water. 30% of the world lacks access to sanitation facilities. They cannot go to the bathroom with a toilet. They go out in the fields or someplace like that, and there's all sorts of risks of disease. That's a lot of people who don't have access to sanitation. 2/3 of the world population is not using the internet, although maybe that's a good thing. Maybe we can keep them away from the internet. No, the internet's good for information. It helps democratize information. It's been good for the economy, and there's a lot of people who don't have access to it. And there are only 600 million cars and 250 million trucks worldwide. That seems like a lot, but there's billions of people who don't have cars and trucks who really want mobility. So those people want those things, and they deserve those things, and what's that going to do to our energy consumption? Well, let me lay it out for you. On the y-axis is the energy consumption per person per year, and then we have population on the bottom. There's about 7 billion people in the world that consume 75 million BTU of energy per person per year. Then there are 60 million people in the United Kingdom. They consume twice as much energy per person as the rest of the world. Then there are 315 million Americans. We consume twice as much as the British. And then there are 25 million Texans, and we consume 60% more than typical American, who consumes twice as much as the British, who consume twice as much as the rest of the world. And in total, we consume about 500 quadrillion BTU of energy a year. So that's the situation today. Well, those people around the world want to consume energy like the British. So if they do, the energy consumption goes up. We go up to about 800 quads of energy consumption. Well, what if they consume like Americans? It goes up again. What if they consume like Texans? It goes up again. Look at all the energy. And by the way, there won't just be 7 billion people, there might be 9 to 11 billion people. That area of green is the energy we need to provide in the future, and that shaded area is the energy consumption today. That means we need to increase the amount of energy we pull out of the ground, move to market, burn, use, and then clean up after. That's a factor of 10 higher than today if we have more people and they all consume like Texans. So how can we bring those good things of energy that we Texans have to the rest of the world without trashing the environment or making it too expensive? That's the challenge for society. Well, to do that, we'll go through transition. The energy world is going through a global transition right now for a variety of reasons. There's population growth, more people, economic growth. Those people are getting richer. As people get richer, they consume more energy per person, and there's more of them, so that's double compounded growth. They're moving into cities, so you have urbanization, people moving from the farms to the cities. They're industrializing, so they're not making just food, they're making products and goods and services. They're manufacturing things, and they're electrifying and motorizing. As people get rich, they prefer electricity and cars, because those appliances are convenient and fun, and they enable us to do all sorts of great things. So people are buying cars, buying electric appliances, moving to cities, building factories, and there's more of them, and they're getting rich. And that's going to drive everything in the energy system. There are a couple technology trends to keep an eye on. One is the decreasing resource intensity. Products and services are getting leaner. Things are going to require less energy. Cars will get more efficient with time. Engines and motors will get more efficient. Factories will get more efficient. This is a good trend. So we're using less resources to achieve the same things we used to do. They're also getting smarter. We have increasing information intensity. Products and services will have more data, big data, lots of data around. We'll have data servers and data centers. We'll have computers and internet, and we'll use that information to make things leaner and make it cleaner. So that's another trend. And the third technology trend is increasing customization. Products and services will become distributed. We'll make them on site for ourselves rather than depending on a faraway power plant or water plant or even grocery store or even a hospital. We'll do that at home. So let's go through some of those winners. Well, things like on-site energy production with solar panels. It'll be done on-site. It'll be smarter. It'll be local. We won't depend on the faraway power plant. Or on-site water harvesting and maybe even treatment rather than depending on a faraway water treatment plant. We'll make our own things. Why do we need a factory? We can have a 3D printer. We'll just do it at home. We'll make custom things. Instead of having mass production where everyone gets the same thing, we'll have mass customization. Everybody will get their own thing, which is kind of cool to think about. And then we'll even have on-site healthcare. Why go to a hospital when you could just send the data, scan your body with the right kind of technology and send it to the doctor and get the diagnosis that way? Why have a centralized hospital, a centralized power plant, water treatment plant, or factory when we could do it on-site for cheaper and smarter and with less resources? So those are technology trends that will take us to our energy future. And we put them all together. The good news is you have increasing democratization of resource decisions. That will liberate society as a whole, I think, which is good news. We're going to get to a cleaner, greener, brighter, more liberated energy future, which is part of the desire. How do we use energy to get all the liberty of energy without becoming a slave to the energy system? How do we have energy liberate us instead? So we can get there with some better decisions. But what do we do while we wait for new technologies? We need to buy ourselves some time. My daughter, Evelyn, who was 7 years old when she said this, she's now 15, and she doesn't really talk to me much anymore, but she used to talk to me, and we'd brush our teeth together. She's up here scowling at me right now in the front row. So we used to brush our teeth together. Embarrassing now. I'm sure she'll be very angry later. So we used to brush our teeth together, and every night as a nightly ritual, we'd put toothpaste on our toothbrush, we'd turn on the water, we'd turn off the water, then brush our teeth, and then turn on the water again. And we would turn off the water while brushing to save a gallon or two of water, which is a good conservation practice. And you should all do that. By the way, that doesn't save that much water, but you should do it. You should really quit watering your lawn is what you should do. But conservation matters at every scale. I didn't turn the water off fast enough once to her liking, and she made a fist and looked at me and said, "Turn off the water, Daddy. The scientists need time." And I was really sort of blown away by that. It's like, that's right. Conservation buys us time. And that's the key. So I appreciated that insight. Sometimes the kids have the better insights, right? We should listen to them. And the key about conservation is it works at many scales. It works at every scale. You can turn off the water when you brush. You can turn off the lights when you leave the room. At a larger scale, you could drive an energy-efficient car, maybe not water your lawn, and you could reduce, reuse, and recycle so we don't have to manufacture as many goods. At large scale, we can redesign our cities so they're more compact and smarter so we're not spending so much energy driving back and forth, and we can get things done in a more intelligent, clean way, and maybe we can make our power plants more efficient, and we can redesign society. So conservation works at every scale, and it buys us time while we figure out something better. The challenge is we need people to do all that. The world needs resource-conscious people who can lead us to a better path, and that is you. Thank you very much. Thanks, Jim. We got time for Q&A, right? Yeah. Is that on? And we got time for questions and answers, but you have to come up here to the mic. We want you on the mic. So you might have to move. There you go. Come all the way across. Or if you have to come down this aisle and around, that works also. Good questions might go on TV, so just heads up. And I'll do my best to answer them. Is the mic on yet? Is it on? Did you get it? I don't think it's on yet. Is there a switch right there at the top? I'll repeat the question with my mic.
Is it theoretically possible for gasoline to be completely replaced by hydrogen fuel?
Yeah, I'll repeat the question. So is it theoretically possible for gasoline to be completely replaced by biofuels or by solar power is the question. Why don't you ask the question again now that the mic is on?
Is it theoretically possible for gasoline to be completely replaced by hydrogen fuel or solar power?
By hydrogen fuel or solar power.
And how much would it cost?
Yeah, so, oh boy. So can gasoline be replaced by hydrogen fuel or by solar power? And the answer is yes, it's theoretically possible. And the challenge is, well, how much will it cost? So let me talk about hydrogen. So gasoline we can get from nature. We can go get crude oil, petroleum, then we can refine it. We boil the oil and we get kerosene and diesel and gasoline and tar and wax and different things. And about half that barrel is gasoline. So we get gasoline from nature with a little bit of effort. And that gasoline is a great fuel because it's very energy dense. We have a lot of energy in a small amount of volume and a small amount of mass, which means it's great for transportation. It's great for cars. So we can use that for mobility. Hydrogen doesn't exist naturally in nature like that. We can't mine for hydrogen or drill for hydrogen. We have to make it from something else. So we have to get natural gas, or we have to get water and split it apart and split off the hydrogen. So it's not you, it's someone else up there. So if we take natural gas, we can turn it into hydrogen or water and split it into hydrogen. So we have to work harder to get hydrogen. It takes a lot more energy to get the hydrogen, which means it's going to be more expensive. Now, there are some termites that have 3 guts, and their hind gut makes hydrogen. So there's actually a natural way to make, so we could like get billions of termites and squish them with a steamroller and capture all the hydrogen maybe. But that's pretty expensive too, maybe not good for the termites, you would say. So,
well, it's obviously not good for
yeah, so something to keep in mind. So hydrogen could be done, but it's really hard to do. And it tends to have low energy density. Hydrogen's a light gas, so it needs a much bigger fuel tank. So the fuel tank in your car would have to be much bigger unless you have like a very fancy ceramic device that holds the hydrogen. So that makes it expensive. Now, could you replace it with solar power? Yes, you could use solar power to make electricity that you put into a battery. And that battery could be at your house or in your car or something like that. And you could use that to replace gasoline. The challenges with that, although it's pretty efficient actually, are that the batteries are expensive and heavy. So it's expensive for the battery, although the electricity is cheap. And then you have a heavy car you're dragging around, so maybe your car only goes 200 miles, whereas your gasoline car goes 400 miles. So there's some challenges with electricity, but you could do it. It's just expensive. That's where we need the energy breakthroughs to happen. Great question. Thanks. Next, yeah. You're getting applause. That's great. So,
what do you think the energy is of the future? Nuclear, solar, turbine? What would your be?
What's the energy of the future? That's a great question. So, great question. What's the energy of the future? What do I think it's going to be? It's going to be a lot of the things you said. I don't think we're going to get rid of oil, coal, natural gas anytime soon. I think we're going to reduce how much we use of them, but it might not go to zero because we use coal also to make steel. So maybe we'll quit using coal to make electricity because we'll use solar power or wind or something else, but we still want coal to make steel. And we might get rid of gasoline for our cars, but we still like crude oil for making certain waxes and other things, so we still might use it for some products. So those might decline with time, and I suspect that renewables will grow, like wind and solar and geothermal and tidal energy and other things like that. I think natural gas will grow for many decades and replace coal for a while. And I think nuclear will also come in the long run. But there might be things we haven't even thought of now in the next 100 years where you have examples in nature. You have electric eels, animals that give you electricity. Maybe there's a bio way to get electricity directly. And we talked about the termites with hydrogen. Maybe there's some natural way to make hydrogen. So in the far future, who knows? But I think in the next 30 years, it's going to be mostly the same, but less of the fossil fuels, more renewables, maybe really with natural gas filling in the middle. And then as we get farther in the future, nuclear renewables. Then after that, something really clever, and I hope you think of it.
So you don't think we're ever going to get rid entirely of natural gas, coal, or?
I don't think we're getting rid entirely of coal, natural gas, and oil in the next few decades. But I think by about 100 years from now, it'll be close to zero. And the oil companies say the same thing, actually. It's very interesting. Yeah, great question.
How can can and any kid actually get out there and help?
That is a great question. How, in addition to concern, thank you. Yeah, that's a great question. I'm going to tear up. That's a great question. So what can kids do to help? I think that the kids are often smarter about this than the adults. So talk to your parents about their wasteful habits is what I would say. Next time they argue with you about doing chores, say that takes more energy than playing video games. I'm just kidding. Don't do that. No, the things you can do as a kid is learn as much as you can about energy and recognize that you have decisions to make about energy. You choose whether the light switch is on and off, whether the faucet's on and off. So you can make a lot of conservation decisions every day, several times a day that you have control over. As you get older, you have decisions over what kind of car you'll buy or whether you'll buy a car or ride a bike, what kind of house you'll buy, whether that house will be close to work or not. And you have decisions about what kind of country you want to live in. So as you learn more and take control over your decisions and then influence people around you, you can have a huge impact. And so conservation is where it starts, education is where it continues, and then you'll be that person who makes the decisions for the rest of us later on. And we're very happy to have people like you make those decisions because we've got a lot of mistakes we got to clean up. Great question. I think next one, yeah.
So the pictures you showed us from space with all the burn off of the natural gas, why in the world are they not collecting that and pumping it?
That's great. So why are we flaring gas when we could collect it or pump it or use it for something else? I would say that first thing, flaring's not new. Flaring was very prominent about 100 years ago through the 1950s or so. There's an old joke in Texas that you could drive from South Texas all the way up to Houston at night without your lights on just by the light of the flares. Because gas was a cheap byproduct. We would drill for oil, which is worth a lot, and then get the gas for free. And if you don't have a pipeline to capture the gas and move it to market, you just burn it. And you want to burn it because if you have gas around that's unburned, a spark could set off an explosion. So for safety reasons, you want to burn it. It's safer to burn it than not. And actually, for the environment, it's better to burn it than let it go. But it's even better for the environment, for safety, to capture it, take it to market. The reason why we flare gas in some places is because they just don't have the pipelines. So in Texas, in the Eagle Ford Shale down south of San Antonio, we don't have the pipelines to capture the natural gas. But in West Texas and the Permian Basin, they don't flare because they have the pipelines. That's the main reason. Do you have pipelines to capture the gas or not? And how quickly can you build them? So they're building pipelines in North Dakota. They're building pipelines in San Antonio. They're not there yet. The other issue is you could just capture that gas even without a pipeline and turn it into chemicals or power or do something on site or boil water even. But that tends to be expensive, or we haven't made the devices cheap enough yet. So we need some inventions to help drive those costs down. Right now it's too pricey. That's a great question. Yeah, next question. They're not going to clap for you because you're not a, yeah, okay, very good. You're, I thought it was a great question. I don't know. Very good. Yes, next question here.
Is it possible to use the greenhouse effect gas as energy?
Oh, that's a great question. Can you use greenhouse gases as energy? It depends on which greenhouse gas. So there's many greenhouse gases. There's water vapor, there's carbon dioxide, there's methane, which is like natural gas, and there's things like refrigerants that come out of different things like our cars, air conditioner, or our refrigerator at home. The CO2, the water vapor, and the refrigerants, they're not good fuels. But the methane, that's a greenhouse gas. We can use as a fuel because that's like natural gas. So if we captured the natural gas from cows burping, or from food decomposing at a landfill or in a compost garden, or from leaks from pipelines, we can use that to stop the global warming, to keep it from being as bad, and we can use it as a form of energy. That's a great question. Okay.
Because I thought that maybe if we use that, we can stop global warming.
Exactly, do both. Yeah, stop global warming and the energy. Great. Next question. You might want to tilt it in. Yeah.
Okay, better.
Good job. Yeah.
If one of those nuclear power plants has a meltdown, could you see it from space? Like
If
the
there's a nuclear meltdown, could you see it from space?
Yeah.
Well, that's a great question. That's a very scary question. Probably, yeah. So I don't know what you watch at home, but
I don't watch anything inappropriate.
you can get a really big cloud, and you can see the cloud from space. And maybe with particular types of cameras, you can see the different radiation. You might not see it with your visible eye, but you'll be able to measure it from space for sure. So nuclear meltdowns, I like nuclear energy because it doesn't emit carbon. It's pretty reliable. It's baseload power. It's pretty clean, but it's dangerous. So if you do nuclear the wrong way, you get big explosions or meltdowns. You can definitely measure it from space. You'll feel it in society. I don't know if you'll be able to see it with your eyeballs, but it's scary nevertheless. Great question.
Okay, I thought they exploded.
Okay, you got the exploding part. Good.
How do you store solar energy?
That's a great question. How do you store solar energy? If you take solar power, photons hitting a solar panel make electricity that can go into a battery. That's one way to store it. You could take the solar energy, which is hot, like you get a sunburn if you're outside because it's hot, to heat water, and you can store hot water. You can store thermal energy. That's another way. You could use that solar energy to drive a pump that compresses air into a tank, and that tank has high pressure air you can release, and it can spin a turbine when you want. So there's a variety of ways. The most typical way, make electricity with the battery, but batteries are pretty pricey. So, but that works. Great question.
Does your daughter say any other things like that?
She does. I won't say everything she says, but she said something around the same time. We did a couple things. I quote her in my classes a lot. She has two things come to mind. One is she wrote an essay. We watched a documentary about oil, and she was 7 or 8, and she was sick. She was like, has a fever at home watching this documentary, because that's what I do with my kids, I guess. And it was about oil and the end of oil. We're running out of oil, and oil's expensive. And she goes, you know what? It's a bad way to go about it. We should use trash. And she went and wrote a 2-page essay as a 7-year-old saying, here's why we should use trash for energy. It would save oil, to save the planet, and be cleaner for us. So she talked about how we should use trash for energy, and that's a good idea. Waste to energy, you can use waste plastic. There are certain types of plastics you can't recycle, like baby diapers. You know why you can't recycle them? Because there's stuff in the baby diaper. So it's organic matter. It's contaminated with organic matter. But that diaper, that plastic in the diaper has as good as energy density as coal. So you can pelletize that diaper, turn it into little pellets, and burn those pellets instead of using coal. That's a form of trash. You can burn trash to make electricity. You can take cow manure, big lagoons of cow manure, and make natural gas that you burn. So she's right. You can use waste to energy. Another thing she said once I thought was really interesting, we're driving in the car off to soccer practice. It's on a weekend. We've been in the car for 30 minutes stuck in traffic. And she goes, I can't wait till we run out of oil. So instead of being trapped in a car, we can be riding our bikes, which is a lot more fun. And I thought that was a really good idea. So for a lot of people, peak oil, running out of oil is a scary thing. But first, like, man, this is liberty. Getting out of this car and not having oil, I'm going to ride my bike. So yeah, she's made 2 other really smart comments over the years. Great question. Thank you.
Can we use trash for energy or in oil?
How do we use trash for energy? So there are a couple ways we can use trash for energy. One is you can burn the trash, and you use that heat from burning it to make steam, and then you have steam spin a turbine to make electricity. That's called a waste-to-energy plant, and we have them. We actually make a lot of electricity in America by burning trash. Not as much as Europe, but we do burn a lot of trash. The other way is you could take that trash, put it in a landfill, and then over time that trash decomposes in the landfill, and it becomes natural gas. And then you use that natural gas as a form of energy for your cars or power plants. So we can do it a couple different ways, or what I talked about with the baby diapers. You take the trash, the pizza boxes, the fibers, the cloth, the carpets, things that you can't really burn or don't want to burn, at least not in its normal form. You put it in little fuel pellets, and then you burn those pellets instead of coal. So there's a couple different ways you can use waste to energy or trash to energy. Great question.
So like before you mentioned that we can use solar panels or stuff like that to generate electricity, and that we might get rid of oil and coal like soon after a few decades. But how are we supposed to like power our stoves and stuff? Because most of the stuff we use to power our stoves are like propane and methane, and most of those are harmful for the environment. Do you have any other like suggestions?
Yeah, that is a great question. So we use a home for heating and cooking, things like electricity. You might have an electric stove, an electric heater, or electric water heater. Or you might have a natural gas stove and a natural gas heater and a natural gas water heater or a propane one if you're on a farm or maybe in an RV or something like that. It's harder to replace the fuels, the gaseous fuels, liquid fuels with electricity. So in that case, you'd use solar panels with a battery and then have an electric stove, or solar panels with a battery and an electric heater, that kind of thing. Or you can make that natural gas or the propane from natural sources. It doesn't have to be from fossil fuels. You can make it from decomposing food, or from decomposing cow patties, or from other sources at landfills. So we can make the natural gas from other ways also. In fact, 40% of our natural gas consumption in America could come from natural sources. It doesn't have to be from fossil fuels. So we have other routes for that as well. Great question.
I was wondering, is it possible that basically, you know how coal or like wood burning power plants, they produce the smoke and other gases when they burn. I'm wondering, is it possible basically when those gases or smoke is burned off of the wood, is it possible to capture it in like a pipeline and redirect it through? That way it comes back around and combines with the steam to help produce even more power.
Great question. So you're an engineer in the future, perhaps. So we have you have fuel come into a power plant, and you have a smokestack. So some heat and some gases come out the smokestack, and some heat goes out the power plant in the waterways. They have water cooling for the power plant. And then a third of the energy leaves as electricity. So coal comes in, a third leaves the smokestack, a third leaves as electricity, and a third leaves the cooling loop. And that heat in the power plant you could use in the smokestack. You could use thermoelectric devices, little devices that take the heat and make electricity. You could also take the hot gases like CO2, capture it, and then use that CO2 to make chemicals or to make materials or even inject it in the ground to get oil if you want somewhere else. You don't have to put it in the atmosphere. You can capture the gases and use them again. We already capture some of the sulfur that's in there. We inject limestone in the smokestacks and capture the sulfur and make things like calcium sulfates that we can use. We also collect the fly ash, the ash that would have flown out. We collect that and make drywall. So the drywalls in this room might have come from coal. And sometimes the bottom ash that comes out of the bottom of the coal plant we use for road aggregate. So you can use the things that come out the smokestack to make materials, and that would be a pretty smart way to go, rather than having mounds of waste out by the power plant or waste injected into the atmosphere. That's a great question.
Other than our love of pickup trucks, what is it about Texans that use so much energy?
So why did Texans use so much energy? That's a great question. So Texans use a lot of energy for a variety of reasons. One is we're rich, and so we have big houses and big cars, and we're in a big state that's very population sparse, so we drive those big trucks long distances, and we're in a hot climate, so we air condition those big homes with a lot of power. That's a big part of it. Big homes in the South need a lot of air conditioning, big trucks driving long distances, and that's a lot partly from our cultural mindset. We're an oil-producing state. The more oil we produce, the richer we get, so the more we consume, the more we produce, the richer we get. We think of consumption as a path to wealth rather than conservation as a path to wealth, which is what a smaller state that doesn't produce oil might say. Those are all contributors. The biggest reason is industry. We have a very industrially active state. We make chemicals, we make energy. Energy is very energy intensive. We make metals, we make food, and so we use a lot of energy just to make things that other states want. So most of our energy consumption is actually industry. And then we also have these big homes, big trucks, long distances. So it's partly cultural mindset, population density, demographics, wealth, an approach to energy consumption, as well as industry. So all those factors combine to make us the biggest consumer by far. Great question.
How much energy has all 94 hot science cool talks taken up?
Well, we can figure this out. So how much energy? 94 talks, right? Each talk is an hour and 15 minutes. I would guess that this room consumes power at a rate of maybe 2 kilowatts, maybe 1 kilowatt. Let's say 1 kilowatt, because there's a computer that's 150 watts. There's several lights that are hundreds of watts. There's a spotlight, which is maybe 150, a couple hundred watts. And then, well, maybe if I include all your phones, it gets even worse. So say a kilowatt. Over an hour and 15 minutes, over an hour, use 1 kilowatt be a kilowatt hour. So it's 1.25 kilowatt hours for the talk tonight. And then we've done that 94 times. So what's 94 times 1.25? Round up to 100, 125 kilowatt hours. And then how much of that was because of your question? We can figure out later. But it's a lot. 125 hours would power a typical home for, I guess, just a handful of days. So it's we usually use, well, we use about 1,000 kilowatt hours over the course of a month. So that energy over those 94 talks is my home for a few days, something like that. So maybe that's not so bad. So we're doing all right. That's a great question. Great, thank you.
So how would we make the switch over to like natural gas or something like that? Because oil might still be cheaper. So like
yes, that's right. Yeah.
People who are like not like poor, like desolate, but like not rich either, like they would still like keep on using or might not have enough money to like buy a new car that wouldn't use that. So
this is a great question. How do you switch from oil to gas when it costs money? Not everyone has a lot of money. And energy is very important for lifting people out of poverty. If we make energy cheap, then it lifts people out of poverty. But if we make it too cheap, we consume too much and it makes us degrade the environment. So how do we strike that balance? And if you want to make the switch from oil to natural gas, the natural gas is actually cheaper than the oil. It's a cheaper fuel, so that would save money. However, you'd have to pay thousands of dollars to convert your car. So you might need to get a natural gas car, and that means a different natural gas tank. The engine's the same, actually. It's just the tank that's different. And some of the fuel handling, that might cost $3,000, and you might not save $3,000 of fuel over the 10-year lifetime of the car. So that's where it gets expensive. Now, that's in the U.S. In Italy, their natural gas cars are like $800 more expensive, and so it does make sense for them to use natural gas instead of oil. They have these natural gas Fiats you can buy, where the natural gas tank is built into the chassis of the car. So if we design the cars the right way, it's not as expensive, and it's a low upfront cost, and that's where we would use like social policy or government policy to help people make cheaper the better decision or the cleaner decision. So we'd use a policy to maybe encourage people. That's one way you could do it. But right now, natural gas is a cheaper, cleaner fuel than oil. The cost is really in the tank in the car. So that switch, and that cost is very important. That switch is important because we don't want to make everything more expensive for people all of a sudden, because that's not good for getting them out of poverty. That's a great question.
My name is Jim Edwards. I'm a civil environmental engineer. Would you care to comment on...
I'll comment on just the fact that you're a civil engineer. Oh, you had more. You had a question. I was going to celebrate you, but go on.
I do waterworks.
Okay.
Care to comment on climate change and emissions from internal combustion engines and jet engines?
Sure. Okay. So the question about climate change and emissions from jet engines and also from internal combustion engines like in our cars. In the United States, cars and transportation of all sorts, including trucks and planes, are responsible for about 28% of all our energy consumption. It means all the energy we consume, 28% of it is just to move us and move our goods around. And that means that it's responsible for a large fraction of the climate change emissions, but it's about 25%. It turns out the power sector uses more energy and emits more CO2, more greenhouse gases than the transportation sector. So about 25% of our emissions are just from our cars and our trucks. And there are a couple of ways we can solve that. We can make them more efficient. More efficient cars, if you double the efficiency of the car, it produces half the CO2. We can switch the fuel for the car, say to natural gas instead of petroleum. Natural gas produces a third less CO2 than the oil does. Or go to electric vehicles. If the electricity is from solar or wind and not from coal, say, then that works out as well. So you can do a fuel substitution or technology substitution at the car level to make it more efficient or use a different fuel entirely. We could also change where we live so that we're closer to work and not driving as far. We make goods locally, that kind of thing. We could change how much we need transportation by setting our society up in a more efficient way. And then we can reduce all the greenhouse gas emissions while still having all the mobility we want. That's the way forward. You also asked a question about aviation. Aviation or planes are a small part of that transportation. I think aviation is like 8% of our transportation, which means just a few percent of our total energy use are for planes. But the planes are up high. When they have emissions, it has a different effect on the chemistry than down low. So it has a greater than 1-to-1 effect, say, compared to ground level CO2. So we have to worry about the emissions for a variety of reasons related to complicated atmospheric chemistry that I'm not sophisticated enough to know the answer to. But it is different for aviation than for our car on the ground. Overall, about 25%. Great question. Thank you.
Thank you.
Michael, let me interrupt here. Just no more people get online because Dr.
Well, if you're in line, that's all right, but don't go to the line. Yeah.
Let me interrupt here. There's a question from someone.
And I'll repeat it on the mic. Okay.
Scientific Americans. Who is your favorite historical electrical inventor? What did you like about him or her? That's from Jack and Carter.
Jack and Carter through Scientific American. So who's my favorite electrical inventor and what did I like about him or her? Wow, there's so many great inventors and great names. Names like Edison and Watt and Tesla and Joule. Great names out there. Westinghouse was a good one. Maxwell might be the best one. So there's Maxwell's equations that give us the theory for electromagnetism and electricity. Great thinker, reinvented physics in many ways. So I would say Maxwell's the greatest thinker when it comes to electricity. Didn't really invent stuff, just gave us the scientific thinking for how to do it. My next favorite one wasn't really electricity, it was really Watt in making the steam engine good. Making the steam engine, taking coal and burning to make steam and making it drive pumps, making it more efficient was what Watt did. That's why we named power, the unit of power, the Watt after him. Without Watt's improvements, we wouldn't have gotten to electricity. So with Maxwell and Watt together, we got there eventually. So those are my two favorites. But there's also people like Tesla who were brilliant, invented many things, or Edison, or even today, maybe people say there are others who are inventing better batteries. The inventor of the lithium-ion battery is actually John Goodenough, a professor here at UT, who's in my building over mechanical engineering. There are great inventors alive today. Yeah, that guy, he did two things. He's changed the world twice. He invented the lithium-ion battery for electric vehicles. He also invented RAM, random access memory for computers. Yeah, wow, to change the life for the world once would be amazing. To do it twice, that guy's amazing. Great question. All right, next question here.
Oh, okay. Well, this has been on my mind for like a really long time now.
Oh, wow, okay.
Yeah. Like, I always wondered as a kid, like, oh my gosh, oil, there's so much of it in, like in America and things. I always wondered when we run out. I wanted to ask you, because, like you're an expert. And
oh boy.
Yeah.
When are we going to run out? Is that the question?
No.
Oh.
Like, is there going to be like a war on energy? Are people going to like fight over countries?
Are people going to fight over countries for oil? I would say when are
energy, basically.
I'm going to ask this way: when will people stop fighting for oil? So, I think this is a great question. So, as oil gets scarce, or as resources get scarce, people fight over them. We have fought over oil.
Yeah.
We have openly admitted that oil is an important part of our national security and our policy. The first Persian Gulf War in the early 1990s, which I think you were not born for, or not alive for, we had an oil war, and President Bush said this is a war about oil. We have fought over oil. In World War II, we were attacked by Japan. Japan attacked us over oil because we had an oil embargo. People don't realize that World War II was an oil war, that we were attacked because of our oil policies with Japan. And then a lot of the movements of World War II were taking over countries to get their access to their coal or the oil. We still do it today. Countries have fought over water. They've also fought over salt. Salt, why do we need salt? To preserve foods.
Like minerals, basically.
Yeah, minerals. So we used to fight over salt to preserve our food. If you didn't have salt, your meats would go bad. So we used to fight wars over salt until something better came along, electric refrigeration. And isn't it interesting? So with electricity, a better technology, better fuel, it was cheaper to preserve the food. It lasted longer. The food tasted better because it wasn't as salty. It was a better solution. It reduced the need to fight wars over salt. And then, you know, the funny thing that happened? We found plenty of salt. We always look for salt on the surface, but we found salt domes deeper. So now we're awash in salt. Salt's very cheap, but we used to fight wars over it. So now we fight wars over oil. It's very expensive. Maybe we'll find a solution to the oil problem, which might be electricity again, by the way. We won't need oil, and then we'll find a lot more, I bet, just like with salt. So great question.
Awesome.
Will we fight wars over it? We already are. I hope we stop sometime soon. That's a
Yeah.
great question. Thank you.
So I was just curious, ever like today, we saw the hydrogen bus that is clearly fueled by hydrogen. Are we ever going to like replace like diesel fueled buses with hydrogen buses because of the CO2 emissions from the oil?
Great question. Will we ever replace diesel buses with hydrogen buses, maybe a fuel cell, or you can actually burn the hydrogen in the same engine that you burn diesel in? You can burn the hydrogen or use it in a fuel cell. Well, we've already replaced one, the one you saw, the hydrogen fuel cell bus. Diesel, when you burn it, releases CO2. Hydrogen, when you react to hydrogen, it makes water vapor. So hydrogen is sort of inert or benign for the environment. It doesn't hurt the environment the way the CO2 does. And can we replace it? Absolutely. It just takes money and some more technology. And the costs are what making people kind of nervous. It's also hard to get the hydrogen. It's hard to produce hydrogen. You have to break it out of the water, or you have to turn natural gas into the hydrogen. So it's expensive to make the hydrogen and then expensive to use it, but we could. And people are starting to experiment with that. You could also replace diesel with natural gas. So there are a lot of trucks, big trucks, they have big diesel engines. They're now using natural gas because the natural gas is cheaper and cleaner, so that's another way to go. Electricity is hard to do with big trucks because electricity requires big batteries. So you want a more dense fuel like diesel. So I think we're getting there, and it's going to happen. It's just expensive, and we need better technology.
So, like, in your opinion, would you rather take diesel or hydrogen?
If I had hydrogen with a safe way to store it, a safe, clean way to produce it, an engine to burn it in that didn't leak, I would prefer hydrogen. And I'll tell you, I got my PhD in mechanical engineering burning stuff. I used to burn stuff for a living. If you're ever really bored and want to know what to do, go get a PhD in mechanical engineering. They'll let you burn stuff. And so we used to burn things like natural gas and hydrogen. And the thing about hydrogen that's kind of scary is when you burn hydrogen, the flame is clear. It's not blue. Like natural gas has a blue flame. Logs have an orange flame. Hydrogen has a clear flame. You can't see it when it's burning. And that makes it a safety risk because when things are on fire, you want to know where the fire is to put it out. But if you don't know where the fire is, the hydrogen, until you feel it, it's too late. It's very dangerous. Also, the hydrogen is very light. It leaks very easily out of pipes, so it's hard to keep it in the pipes and tanks. If we can overcome those technical challenges, hydrogen would be a much better fuel. It's a great question.
Okay, so I was just wondering, what's your favorite element?
What's my favorite element?
Yeah.
Can I answer what my favorite molecule is instead?
Sure.
Okay, my favorite molecule is ammonia. But my favorite elements, maybe gold for obvious reasons. I like
Oh,
gold.
oh.
But, all right, good. Yeah.
Gold's my favorite
Gold's
too.
your favorite too. Okay, good. I'll tell you why I like ammonia. So I studied ammonia in combustion. I used to burn stuff in graduate school. I'd burn things. And when you burn hydrocarbon fuels, they give you nitrogen oxide, NOx, N-O-X. And nitrogen oxide is a pollutant that forms acid rain. It can form particulate matter. It can kill you a variety of ways. And if you have this smokestack, these flue gases with NOx in it from burning the hydrocarbons, one way to get rid of the NOx is to inject ammonia. The ammonia reacts with the NOx and makes nitrogen and water vapor. So you can use one poison, ammonia, to defuse another poison, NOx. And so my work in research at graduate school was to invent an ammonia sensor to measure how much ammonia you had in there so you didn't put too much ammonia in there. And you can also use ammonia to make fertilizers, do all sorts of things. So I really like ammonia. That's my reason for that answer. Great question, by the way. And I think we have time for just a couple more, but I'll be here afterwards. But please proceed with your question.
How much power does it take to light a light bulb?
That's a great question. And you know what? The answer changes with time. How much power does it take to light a light bulb? The light bulbs I grew up with, 100 watts. the light bulbs you're growing up with, 15 to 20 watts. Light bulbs today from LEDs are much more efficient. A fluorescent light bulb is like 40 to 50 watts. The light bulbs today use less power and give more light. And it's about 100 watts for the old-fashioned one, 15 to 20 watts for a new one. Great question.
How long does it take to get oil out of the ground?
How long does it take to get oil out of the ground? Oh, that's a great question. So I'm going to give you a complicated answer. If you have to find the oil, and then find the people to drill for the oil, then drill for the oil, it's like 8 to 10 years from first exploration. However, once you know where the oil is and you know it's going to produce, it's like a couple weeks. So when they go to a new well site, a new drilling site, they'll drill down 5,000 feet, turn sideways 5,000 feet. That takes a week to 2 weeks. Then they'll spend 5 days injecting water at really high rates and high pressures laced with chemicals and sand to break open the shale and release shale gas and shale oil. That whole process is a couple of weeks, once you know where it is. But if you don't know where it is, it takes years to find it. So it's maybe a decade or 2 weeks, depending on how you count. That's a great question. I'll stay here and I'll answer until you're done. But this will be the last one for the microphone.
Okay, why can't you take hydrogen from the air and use that?
That's a great question. So why can't we use hydrogen from the air, take it from the air and use that? Hydrogen is in the air, but not in the form of hydrogen. It's in the form of water vapor, H2O. So water vapor has hydrogen in it, and you could take that water vapor and then add electricity and split the H2O and you get hydrogen and oxygen. So you can use that hydrogen that way. But the hydrogen isn't naturally abundant. It's always locked up in water vapor or something else. And we can do it, but it takes a lot of energy in to get that hydrogen out. And it ends up taking more energy in than the energy we get back out of it. So it's expensive, but we could do it. There's plenty of water vapor and there's plenty of hydrogen in that water vapor.
So it would be better to just do it from water originally.
Yeah, well, yeah, or you could take fresh water from lakes. There's a lot of places you could do it, but it always takes energy in to split that hydrogen off, and that's the challenge. And right now, our electrolyzers, the device that we use for electrolysis, where you put electricity in to split off the hydrogen, they're expensive and not very efficient. But as they get better, hydrogen will be a better solution. We can also make hydrogen using the sun with special photolytic splitters. They're called photolytic splitters. They use the sun, the heat to split. You make a really hot concentrated spot. You can split the water vapor that way, just using the sun. You can also use the waste heat from nuclear power plants, but that hasn't really been figured out yet. There are other techniques for making the hydrogen, or like we talked about before with termites. You squish 1 billion termites, get a lot of hydrogen that way. So we need a better way to make the hydrogen from water vapor is the best way right now, but it's pretty expensive. That's a great question. Thank you very much for that question. And, yeah. Great. Thank you. Okay. Thank you. Thank you. Thank you for having me. I'm in good company with Katharine Hepburn, and I will stay here for any other questions you might have. I don't know if you have any administrative comments, or is that? Okay. Great. Thank you.